Super. Hi, and welcome to Brain Trucks, AI and Surveillance. This is the timeline for today. And we have Equinor presents with Einar Landre, which is going on digitally. And we have Jing Shi from DNV. We have Håkon Hukkelås from NTNU. And we have Gard Spreeman and Vegard Elvarsen from Telenor. We in NTNU, we are making these events just to connect academia and companies and students within AI, just to get out the application that those who work with AI can manage with them. And we create like Brain Trucks, like here today. We have other events like Startup AI, Hackathon, ADX Brain, and Workshop AI, and Panel Debat, which coming soon. Yes. So for today, the topic is AI and surveillance. We have 4 lectures, as mentioned, and we have this all with start off by Einar Landre from Equinor. So the word is yours.
Thank you very much. Okay. Sorry about it's not the COVID, but something else. But okay, I basically was invited to talk about some work we've done I call it gamification. And basically, I share what we've done, and then you can ask questions as you like. So the first question, of course, is that what does the game of Go share with business? And in reality, it's about one thing. It's basically it's about complex decision making in a really uncertain environment, and where you basically have trillions of possible moves and counter moves. And how to navigate in this sort of complicated decision space is where we basically have put some of our efforts. So what's the value? The one thing we've seen clearly is that it eliminates or reduces the impact of opinions. If you think about people sitting down and discussing, should we do this or that, it's always, it easily ends up on opinions. The facts are neglected. Often the person with the strongest voice, highest seniority will win the discussion. Another thing we have seen is that it enables exploration of some of the solution spaces. And we are then also able to study the impacts of the rules that we have applied. I will come back to that as an example. Another thing we discovered is that it gives us a systematic learning. When you run through this, of course, this sort of board, you see, okay, I chose this one, but what can the effects be? And you have this sort of sharing. And we think it also can offload humans from doing the boring, tidy work and to do the more interesting stuff. So it basically boils down to more money. That's the end. But also happier users. And so it's a win-win. I also want to reflect on another thing, which maybe it's not directly relevant, but it's something called finite versus infinite games. And of course, we have a lot of, finite games with their fixed rules, there's tight boundaries, and there is a winner. Chess, football, projects, campaigns or whatever stuff, tactics, you call it. We all know have a good understanding of the finite games. Infinite games is a little bit more different. There you have adaptable rules. There is no end, or at least within the horizon of what we need to bother about, and there is no boundaries. Being a practitioner of martial arts, basically the daily practice is an endless journey, always something to improve. Continuous marriages or private relationships, same thing. if you want to stay in the game, you need to work hard to improve, whatever that means in your own context. Business the same, and strategy the same. So it's basically to have this mindset of playing to win versus playing to improve. And when we talk about gamification, it's a bit of both. One thing is to, of course, to figure out what's the best thing to do, but it's also about understanding how, by figuring out what is the best thing to do now, is what brings us forward to an improvement in the longer run. So it's about balancing the short-term tactics projects with the long-term strategic objectives and how we try to steer ourselves toward those long-term objectives. Okay, when we talk about games in this environment, we easily end up with choice theory. Basically, how to choose which solution is best. And of course, the hard part is basically where does we land ourselves on the theory of choice theory and rational agents. And of course, and then we can use some of the theories, and we need to have criteria. And a criteria is basically a representation of our. Come back to an example and illustrations of that. And also we need to be aware of how agents learn. And there's basically two principles of how an agent can learn. Is one, it can be given a predefined model, a program model, where basically that defines whatever they want to achieve. But for a lot of problems, such models are inherently difficult to make. The complexities grows out of hand. The other option is, of course, to train the agent with examples using statistical methods and learning algorithms and hope that the agent adopt the preferred behavior and have their. And of course, for those who have experienced machine learning over the last, say, I would say a decade, but the last decade, see that this training with data has proved itself to be a very strong way of teaching how an agent should behave. And basically establishing the criteria and training the agents is then an important task in what we do. So the process we follow is like this. We try to establish the game rules and go together with the rules, the likes and dislikes. We have a scoreboard. And then you have the agents, that is basically the AI, similar agents as used in the game of Go and in DeepMind and these sort of, say that sort of challenges, train them, and then try to put out and find the best possible ways. And then, of course, adjusting on the score system, adjusting on rules, we are then able to, okay, yes, we think this is given the circumstance we have, this is the best decision or best move to do. In our world, we have, of course, it boils down to answering questions. And the question we have addressed the most is basically what's the next best well to drill on the field. And that's and for those who are not used to, say, the oil industry and some of course, to find the best possible well is an NP problem in the computational term. There is an infinite number of options how you can do it. And you think about it, what it's all about is you have a start point, a point on the, basically on the, say, where the platform is, if you put it that way. And then it's about finding the best way to a specific coordinate or place or the, say, area in somewhere inside Mother Earth. And you want to know, and you then need to basically take into account what's already there, what do we know about the underground, and the rules. So of course we want to either maximize revenue from the well, reduce cost. What are the constraints we have? For example, one way of measuring the good side is to say, okay, the number of meters we are able to penetrate in the reservoir section, that's a good measure. If you have a length of 1 meter, you produce less than you can do with 10 meters. We need to deal with the hazards that we want to avoid. Typically, in our case, it's a lot to do with geology, faults, and if you come with the wrong angles into the faults, you risk to get stuck, and to get stuck costs you easily 50 million NOK. So you talk about big money, and you can say the price tag for a well is in the 200 to 500 million range. So of course, designing a well that doesn't produce in itself is also a rather expensive exercise. So there's a lot of constraints, and where we now are able to go from strong opinions, I believe that this is the best thing. No, I don't believe that. It's a better place to go here. Now we are able to basically represent these opinions as articulated rules and see how they come into play when we score them against each other. So if we made one, this is a simplification just to illustrate the point. Of course, we have some sort of reservoir place where we want to place a well or wells. And basically we need to take into account in the geology, things related to drilling, basically the status of the machinery, the platform. Should we stop a well from that's already produced, but it's in its end, it produces 90% water, but it's maybe better with 10% remaining oil, might be better than maybe go on. So should we risk losing that 10% for something that we think is better? And of course, when it comes into the design concerns, you have the length of the well, of course, and the longer the well, it's basically as you can say, a well is a tunnel, and a tunnel of 100 meters is basically cheaper than a tunnel of 200 meters. So of course, short tunnels is good for business, at least cheap. We have this called the dog leg, that is basically the maximum curvature that the steel can have, how you can bend. And of course, that's a function of itself, and it's the diameter of the drill bit of the drill string. If you think about an oil well, it's basically you start out with a big hole, and you put a smaller hole, and you have a smaller hole. So we have this sort of pipe-in-pipe system that you go from 30 inches down to basically 8 inches area. And of course, the production profile. So you need to put all these things in together, and then what you get out is then a list of feasible wells. That's how the game system works. And how do we want to communicate with this thing? It might look like this. This is from one of the fields in the North Sea. It's no secret, it's Gullfaks, so nothing here. All the red stuff, that's existing wells. So it's like a Swiss cheese in that underground. And then you see the white lines here are basically possible routes from a kickoff point in the in the top, and then how we can reach a specific point down below. In this case, it shows all possibilities, because if you look at some of these wells, they are really they are with loops, and those will never fly, but it's not possible to drill them. But then by using these sliders over here, we are able to tighten the constraints. And what we've seen from an efficiency point of view, it's better to generate a lot of possibilities and then narrow down afterwards versus testing each against a very rigid set of rules. The number of if-then statements becomes extremely complicated if you do that afterwards. So filtering is a technically easier way and cheaper compute cycles. So you can then say navigate and play around with this stuff. And what you really do is to try to bind the start point with its end point. And I'll give you an examples that we have that's not from us, but from others that done this. They started out with the problem is that's from the Middle East. So the problem is that we know where we know where we are in the underground, but what's the best point on the surface to land the well? And then they have basically cities and other buildings that you want to avoid. So they have this. You can go both ways. You can go from the target to the surface, and you can go from the surface to the target and find basically the options. You can, of course, we started out with those trajectories because we thought that this is done manually today, which means that we are typically able to say for a target slot combination, we are able to assess 4 options by hand. Now you can assess, say, in the practice, millions. We have seen that others, you can do the same with, for example, investment portfolios. You can just say, okay, what are the attributes we like with the project, and what are the attributes we dislike with the project? And then in the same way, create a scoreboard where you rank your investments. You can also do the same for strategy for an oil field. Of course, over its lifespan of 30 years, maybe you want to drill a lot of wells, but what should be the sequence? What should be and then you can then basically, okay, given that I have drilled, say I need to drill maybe 50 wells, 100 wells, maybe more over its lifespan. Okay, what should be the sequence, and what looks like the best plan? I'm able to assess the whole before I start out with the details. A lot of opportunities. Last thing, of course, one thing is to have this sort of picture. Another one is that you can then start to create interesting combinations and look at your data from different ways. And the interesting thing here with this was done for a particular this one is basically we tested, okay, if we say accepts that we can have a different, okay, here you are bound by the existing infrastructure, but say that we are free to put something on the ground at a subsurface development, then we are, okay, it comes out with a higher production, definitely, but also to a much higher price. So it's, and sometimes this might be a feasible thing to do. And of course, then you can go in and you can discuss the rules and go on and go on. So I think this was my last slide. So just to give in, so what I've basically been showcasing is that, yes, it's possible to gamify business decision making. Here exemplified using, say, a design, a well design as a case, but it's just as applicable for any type of thing where you have different options and want to have them ranked and played out against each other. Yeah. Thank you. That's questions. Yeah.
Thank you so much, Einar. And now we're going to have a Q&A session about 5 minutes. So if you have any questions for Einar and for gamification. Any thoughts?
Do you have any numbers on how well your choice of wells have been optimized after applying this gamification?
You can say we did the first test we did. We discovered that yes, we found we've not done any measurements like that, but we discovered that yes, okay, the subject matter experts said that one we had never thought about was possible, and that sort of aha, that is one of the at least discovered benefits. Another thing we discovered is that yes, they started to say, okay, as one of the engineers said, that suddenly this becomes fun. I'm able to understand the relationship between, if I go out here and you have this glide by the dog leg, basically the angles here. If you narrow that down, you see that the number of options is reduced. So we piloted the solution this summer, and we decided based on the experience from the pilot to extend it and use it to rank the next big, say the annual process that we run on. Okay, what should be the wells to drill next year? And the challenge we have, of course, is that the oil price is volatile. Some say that's a great thing, but of course, when we narrow down, say that we need to have wells that are profitable at different levels, that can be part of the equation. So you suddenly see that, oh shit, those candidates are just, they will never be profitable if the price is so and so. And we have another one also from on the very old fields that are close to basically be shut down. They said that okay, the day we tell the Norwegian government that okay, this is the last oil well on this field, now we are able to say that we have tested all possibilities. There is no options left. It's just so much spaghetti down there that it's impossible to get something through in a piece that is feasible. So you can use it for many things, but you are not measured.
We have another question here.
Yeah, can you say something about the algorithms that you use to find these best wells? So do you just try out every possible setting and then find the best, or do you do something more clever?
Yeah, that's a good question. No, I think that we started out with, so we worked with an external company on this. It's a small startup in Holland called Whitespace Energy, and they started out with it's based on the search tree and strategies for searching in the space. That's basically what we started with. And we have tested reinforcement learning. And the interesting thing is that that works, and it has now last time this summer, it has the same performance as the search tree combination, the search tree approach. So it's very much, if you want to say the best way to is basically to go to AlphaGo and the algorithms used to play. I say how AlphaGo was made to, but basically beated the human players by finding better strategies in that enormous, almost, I think it's 10 in 173 more options than there are stars in the universe and things like that. It's beyond recognition.
Thank you very much, Einar.
Yeah.
Now we're going over to Jingxi from DNGL and her new and severe digital risks of artificial intelligence.
Hello? Hello, hi. Can you hear me? Hello?
Yes, we can hear you.
Okay. Can you see my screen? I'm sharing my screen now.
Yeah, we're seeing.
Okay, great. Okay, so good evening. This is Jingxie from DNVGL Group Technology and Research. It's a pleasure to be invited and give a talk today. The theme of this evening is AI and surveillance. And AI has been a very hot and exciting topic in the last few years. And of course, we all believe it will continue attracting more attention and interest in the future. But today I'm going to talk about AI from a different perspective. That is about new digital risks arising from rapid development and deployment of AI technologies. So I will very briefly introduce Dingwei Jiao's main services and the Department of Group Technology and Research. And then I will introduce two risks currently, like my colleagues and myself are concerning and working on. And in the end, I would like to answer your questions and hear your feedbacks. So a very short introduction about myself. I work for Dingwei Jiao Research Department since 2011. Before that, I pursued my PhD at Telematics, NTNU, and I'm from China. I worked for Siemens before I moved to Norway. DNV GL's main services are related to risk management and quality assurance, so it's not surprise why I'm talking about risk. So we serve customers in a very wide range of industries, from maritime, oil, gas, space, automotive, healthcare, food, beverage, and energy supply chain. And our main responsibility is to identify, assess risks, and also help our customers mitigate their risks. The Department of Group Technology and Research is dedicated to explore emerging technologies and develop strategic insights and foresights to prepare our customers and ourselves for the future. We heavily involved in various scales and types of research and innovation projects through both national and international collaborations. So AI is not new. It has been developed for several decades. And today we are really surrounded by AI-based services, systems, products, and we really enjoy the convenience and the better quality of service provided by those intelligently digital assets. But as the rapid development and the deployment of AI technologies, are we properly aware of the potential consequences when AI is penetrating our life, work, and society? Do we have enough knowledge or good understanding on what would be the potential risks of using AI technologies? So I would like to dig this problem a little bit more. Due to time limit, I'm not able to give you a very comprehensive risk map for AI technologies this time. I'm going to introduce only two risks which we are currently working on. And as you know, AI technology is still developing dramatically. So we have to speculate that AI risks will evolve accordingly. I think most of you have heard about this Uber autonomous vehicle crash accident happened on 18th March 2018. The safety driver was charged with negligent homicide last week, but the investigation report actually revealed very severe safety issue of Uber. So that means inadequate safety culture, need for safety risk management requirements for testing automated vehicles on public roads. And in addition to this, the more detailed technical inspection reports actually discovered the self-driving system software classified the pedestrian wrongly, and it kept changing the classification results. This led to the self-driving system did not respond in time. Why this could happen? Because AI models, or like machine learning models, are typically prone to errors. This also reveals a very common issue of AI systems, that is, the decisions made by AI systems are not justifiable and explainable, especially those complex AI systems, because the advanced and complex AI systems, such as deep learning models, they are developed from combination of like efficient learning algorithms and the huge parametric space. So we can hardly obtain detailed explanation of their behavior. This case should alert us when replacing any critical functionalities with AI in complex systems, especially mission-critical systems. We have to properly design the interaction between AI and the other parts of the system, and it requires we have sufficient understanding on the AI technologies being used. It's not only about the strength of the technology, it's also about the weakness. DNVGL offers a variety of services towards maritime sector. As technology develops, we also need to develop or upgrade or update our services in order to manage risks arising from building and operating new types of maritime systems. So since autonomous shipping is high on the maritime sector's agenda, so we also dedicate extensive resource on researching autonomous ships. So have you heard about the Revolt, developed by DNVGL? It's a conceptual unmanned short sea vessel powered by a battery. It has been served as a platform where many master theses and projects explore the new technologies and the new types of devices. And on Revolt, we have implemented a situational awareness system with some core functionalities and with some different types of sensors. So here shows a very simplification of the situational awareness. So we use the deep learning neural network based object detection model as the core part to observe and detect the obstacle in the neighboring area. And this object detection model results will be used together with other types of sensor data, such as LiDAR data, to provide input to the obstacle avoidance, and then Revolt will react to the obstacle. And here we face the similar risk as the autonomous car. If this object detection model misclassify the obstacle, or mislocate the obstacle, or even neglect the obstacle, what dangerous situation the unmanned vessel will be in? And if we know there is such risk, and what safety barriers need to be in place in order to mitigate it. And there are so many unknown issues, and we need to research. So we have initiated research projects on assuring machine learning models, which are part of digital systems. And it's a very critical aspect to identify the specific operational scenarios where those digital systems will be used. For example, you can imagine the operational scenarios of autonomous ships are very different from operational scenarios of autonomous cars, right? Because the ships sail in the water, but the cars drive on the road. The environmental situation and the regulations for those systems are very different. So it's not straightforward to directly apply the results obtained in other industries to the maritime systems. And the development of autonomous ships is still in an early phase. And currently, we are also researching and exploring what could be the proper tools, methods, and processes to assure AI-based maritime systems. Now we are talking about some exciting part, because today you don't need to be an ML expert. You can start to try out machine learning models yourself. You can pilot your own applications, your prototype. There are so many open source frameworks providing you the APIs of training models. And there are also a lot of the publicly available data sets for facilitating the ML model development process. It provides us the data source to train complex machine learning models with millions or even billions of parameters. But this also actually triggers the new cyber risks of using ML models, especially the pre-trained ML models. So there are no publicly recorded large-scale cyber attacks against AI-based systems yet, but researchers have discovered some critical vulnerabilities of AI technologies. So it's natural to speculate that the hackers sooner or later will exploit those vulnerabilities of AI technologies, and they will target to AI-based systems. So one of the very active research areas is about adversary attacks against machine learning-based systems. So there are very common ways, like if you manipulate the input data, then you can lead the machine learning model to make a mistake. For example, you can misclassify the input data. And you can also poison the machine learning model by contaminating the training data, or you can change the way the learning algorithm learns, especially for these open source ML models and these public available data sets. It will make this poison attack more feasible. And the model extraction attack is a way is to steal machine learning model that has been made available to query. For example, machine learning as a service. So the attacker typically use the API to send inputs to a machine learning model, and then they observe the model's predictions. By repeating this operation many times, so the attackers may be able to retrieve or recover the model's internal details. Here are some examples about the adversary attacks against the computer vision models, because the ML-based computer vision applications are so pervasive. I think the top left corner shows a very famous example. This originally from the most cited adversary example paper written by Goodfellow. So that is by adding a very small imperceptibly noise into the original image, then a well-performed GoogleNet image classification model misclassified a panda as a gibbon. The bottom right corner shows by example. You can even just print out an adversary example, and you photographed using your mobile phone, and then still can cause the well-performed classification model misclassify a washing machine as a safe deposit box. The right-hand side figure shows a physical attack. So that is by painting some patches around lane in the real road. It caused the lane detection function of Tesla's autopilot does not detect the existing lane. So you can see how easy to launch a physical attack in the real world, and it will not require too much effort for the attacker to really launch such attacks in the real world. So following those research work, we may also ask, will the maritime system face the similar cyber risks as more AI technologies will be integrated into autonomous ships? Once we know the vulnerabilities existing in the widely used AI technologies, we have to understand how to assess those risks and study how to define or mitigate them if we know this is a trend to use AI technologies in safety critical systems, such as the autonomous ships. So this semester, we are co-supervising a master project. So the candidate is from the Department of ED, and he will study how to construct adversary attacks against object detection model implemented on robot. This object detection model is ULO, is one of the most popular object detection model implemented in the real applications. And then he will evaluate how the adversary attack can effectively mislead the object detection model to fail. And he will also propose defensive measures which might improve the robustness of the ULO model. And we also expect these defensive measures could be transformed to other object detection models. Since we have seen those potential risks of using AI technologies, and as a risk management organization, we are developing an assurance of digital assets framework. It's called ADA. Here, the digital assets is a very broad concept. AI-based systems is only just a subset of it. This slide shows the current status of our work on maturing this framework. This framework will be applicable to different industries, and it will help our customers to transform their complex ecosystems of organizations, technologies, people, and their social and environment into an ecosystem of trust. We are complementing our existing knowledge on assurance with new perspectives, tools, and methods, because the current assurance practice are not fully equipped in order to build trust in today and the future's complex digital assets, and are not able to build the trust in deploy them in the society. Through working with our customers, we are piloting how to execute this framework in various types of assets, where we need to define the executable process steps. We need to identify new tools, methodologies, and we are going to build a digital portal to host such framework. And in the end, I would like to emphasize trust in AI to drive digital transformation is a double-edged sword. And we need to contribute to not only the technology development, but also to assuring AI will beneficial humans and the societies, not to harm or destroy us. That's all. Thank you. And any questions or feedbacks?
Thank you so much, Ying. Now,
Yeah.
Any questions? Some thoughts or anything?
Maybe not very exciting.
Yes, it was. Else you can ask questions later too, if you want to do.
Yeah. Okay, no problem.
Well, then we have our next lecturer is Håkon Hukelås. He's a PhD at NTNU.
Ska vi se. Yes, funkar micken eller? Okay, so my name is Håkon, and I'm currently doing a PhD at the Department of Computer Science. And what I'm going to talk about today is what I call deep privacy, which is what I worked in my master thesis, which is looking at how you can take a face in an image and then try to replace this face with something that looks realistic, but in this way I'm able to anonymize my identity. Most of you probably don't know who I am. 2 years ago I was sitting at a brain event myself, looking at the presentations, and I'm very happy to be here today. I graduated from computer science here at NTNU last year, where I wrote about anonymization in images. And during my master's, I was both doing an exchange year at UC San Diego, where I specialized in computer vision and deep learning. And I've also been working at Itera and Cisco, where I've been mostly working with machine learning methods. Then I decided to do a PhD here at NTNU, and if anybody has questions about how that is, please answer me after, or ask me after the talk. And one more thing, I'm part of the NTNU Autonomous Perception Group, which is working on computer vision systems for autonomous vehicles. And that's me right there. And my project started with that we wanted to record images in Trondheim. We have this vehicle that we want to record a bunch of images to do research on. And if I start driving around in Trondheim and then recording a bunch of people with their faces, I'm going to have a lot of privacy-sensitive information. So my task in this project was, how can I anonymize the persons? One thing that we want to do with this is that, for example, if we're walking on the street in London, so this is a YouTube video, you're recording a bunch of people. And we want to use this data for computer vision research, So one way to anonymize this data is doing kind of what Google is doing on the street maps, where they just blur out all the faces. But that's very easy for a human to see that, of course, this is corrupted. This face is no longer a face, it's a blurred face. So instead, we want to replace all the faces and to make it still look somewhat realistic. Something you might notice here is that the faces are flickering a lot, and that's mostly because my method is an image-based method. So I'm not looking at video sequences, I'm just looking at a single image at a time. So I'm going to go a bit more technical than the other presentations today. And the system I developed is kind of a two-stage system. So I have this first part that is responsible for detection of the faces. This is really not what I decided to work on, because face detection is almost a solved problem, or the methods that we have today is very good at it. But the second stage of my model is what I call a generative model. And the generative model is responsible to take a face that is already detected, and I first just clip out or remove all the information that might show the identity of the person. You might also see that I'm including a pose of the face, which is just saying where in the image is the different landmarks of the face. So where in the image are the eyes, or the nose, or the ears. Then I'm putting this through, I'll call it a generator now. So it's just taking this input information, this conditional information, and then generating something that hopefully looks realistic. So this, of course, looks like a face, this fake image that I generated, and that's what I want my generator to do. For those who have done some kind of machine learning, this is just a convolutional neural network. But you can look at it as a black box model for this presentation. So if I just assign this network and run this conditional information through it without training it, the original image is going to, or the generated image is just going to look like some corrupted garbage. So this is kind of the thing I want to talk about today, is how can you generate or make this generator learn what is a face? Given this conditional information, how can I generate something that looks realistic, that looks like a face to a human? So for those who have done any kind of machine learning, you know that when you have a neural network, you always want some way to optimize your network or train your network. So you want to define how do you judge your model? And this is something we usually call a objective function. It's something you want to train based on to make the network learn what a face is. So if I have my generator that is not trained at all, I want to give it some kind of feedback on how good it is at generating a face. So we want this objective function to say, does the generated image look like a face? So if you look at this fake generated image, it's obviously not a face for us. But expressing this in mathematical terms is not that easy. Also, I want this generated face to correspond or look similar to the conditional information, the input image or the original image I had. So one way to define this objective function is that I can just look at a patch of the image. So I have my generated image and my real image, and look at the difference. So I can just take a single pixel, and then I can measure some kind of L2 loss or L1 loss. It's just taking a pixel in the original image and the generated image and measuring the distance. So if the distance is 0, you generated exactly the same image. But this is really not a good objective function, and I'm going to show you now. Why now? So I have my one image right here, and I'm going to translate this in two ways. So I'm going to make a blurred version of this image, and then I'm going to take the original image again, and I'm just going to shift it. So you can barely notice the difference right there, but there's a 2-pixel shift. Now, if I look back at the objective function that I just created, this L2 distance between the pixels, and I measure which image is most similar. For example, if I look at these two images and I want to say which image is most similar to the original one, I'm definitely going to select the shifted one. There's no doubt for it, for a human. But this L2 distance is always going to select the blurred one. So this is really not a good measure to say how good an image looks. So this objective function of L2 distance does really not work. So I'm going back to my generator. I have my generator that created some kind of fake image, and I have my real image. One way I can optimize this is that I can look at this generated image and say that, well, this is not a real face because this part looks corrupted. And then I can say that to my generator, and you can optimize it some way. And then you do this again and again and again, and after some time, it's going to learn what a generated image is, or what a real face is. Of course, doing this in practical is impossible. I can't evaluate every image this generator makes. So you change it with something called a discriminator. And this is something known as generative adversarial networks for those who are familiar with it. The way it works is that you take this conditional information, you feed it through the generator that generates some kind of fake image. It might look like a face, it might be completely corrupted, and then this discriminator gives some kind of feedback to say that this image looks real or this image looks fake. And of course, this discriminator has the conditional information right here, so it knows something about how it should look like. This is, of course, going very quick and a very abstracted explanation of what a generative adversarial network is. But if you start to define this objective function right here, and you start to train your network, when you initialize it, it might look something like this. And then you train it over time, and it's going to look more and more like a face. So for those interested, this takes about 20 days to train on 2 GPUs who cost 100,000 Norwegian kroner each. So it's pretty expensive to do this. And that's one of the difficulties of my research. So now I know how to generate a face. I can do face detection. And if you just put all of this together, you have this original image, and I'm able to anonymize this. And this is the resulting image. Again, in a bit more realistic scenario, you have probably a typical scenario for an autonomous vehicle, a bunch of people crossing the street, and this is the anonymized image. And I'm also going to show you a video to show it a bit more close detailed. Oh.
John, you worry about getting wet? I do. But my worry is
So probably the sound isn't good.
Underestimating these guys. And my worry is that a lot of people have been pranked saying that they're going to die. My worry is that you're going to get 10 scripts and that you're going to have dynamite stuff. There's going to be scenes with people you've never had scenes with before, amazing narrative arc. You're going to emerge the hero of the piece. The day after, please find script amendments for episodes 1 to 10. Changes made, you're on it in a single frame of it. All the best.
Is that possible? Could that happen? They could do that.
They can make whatever they want. Whatever they want.
Okay, Sophie, Sansa's been through a lot. Just so much. Before the season...
It's not real, folks.
Yeah.
Annie, no! Oh, sorry.
It is real.
Right, so that's just to give you an idea how this system works currently. It's not perfect, but it's definitely a start to do automatic anonymization. This method has a lot of limitations currently. First of all, is face anonymization enough? So most of you recognize who these two people are. If you didn't see it, it's Trump and Obama. And you know, there's definitely other parts of the body that is able to identify you. Some of the faces are really not looking too realistic, and this is why I'm doing a PhD on it. It's not a master project that is possible to solve in 1 year. Yeah. So all of my code is open sourced. You can search up deep privacy on Google and you should be able to test it out. Next week, I'm releasing a Python library, so you should be able to kind of anonymize an image with 4 lines of Python. So just building the anonymizer, reading the image, and then anonymizing the image. Also, I set up a web server today, so you can test out the system yourself and see how it works. So that's privacy.hukelos.no. And that's pretty much what I had today. I'm going to show you a short demo before ending this. Okay. So I can take any questions if you have it while this is starting. Yeah.
So thank you for a very interesting talk. I was wondering, have you considered like adversarial attacks against your system, in the sense that can I train some network to produce a face mask that when I walk on the street wearing this mask and rob a bank, the Tesla on the street will show you robbing the bank?
Well, that's an interesting question. So, I mean, this, yes, definitely. It's, well, so the question is, so first part of the question is that my system is able to generate all kind of faces. Well, it's not currently, but let's assume that it's able to generate my face on your face. And the second part is that if there exists an adversarial attack. I haven't seen that much adversarial attack on kind of these kind of networks yet, but I'm not sure where the use case would be, because you would. Yeah, but well, I would assume that you had some kind of security cameras that's not anonymizing it. But if you can design some kind of adversarial attack to generate the correct face, I haven't seen work on it, but maybe.
How do you ensure that the face that is generated is not the actual face of the person? I mean, if your generator is good enough, it could probably get closer and closer to generating the actual face.
So in my work so far, I haven't looked at this specifically, but there's work at the Technical University in München that has looked into, first of all, you generate some kind of ID for the person that the original image had, and then you make sure that the generated face is not similar to this ID. So you're using some kind of face recognition software to generate this descriptor of the face, and then you make sure that the descriptors are completely different. Yeah.
Well, about the face mask robbing, just if there's some random element in the way you generate it, because as soon as there's something random, they wouldn't just recognize it and then just start, making the same one. As soon as there's some random element, you would never be able to reliably rob banks with masks and just like gamble on it making the correct face. So I mean, that's not the hardest one to solve, at least.
Yeah. So can I take 2 minutes to show the demonstration?
Unless you want last question.
Oh yeah, sure. Yeah.
Yeah, you choose.
Well, yeah, let's take the question.
Yeah, it's related. So in the video, there was some continuity, even though you said that you did a picture at the time. So it's picking up some kind of context from the kind of the rest of the head.
Yeah. So the way I created the video is that I set the same. So I have a vector that says how the face is going to look. which is just a bunch of random numbers, 500 random numbers, that is going to say something about how the face is going to look.
Okay, so that is
So in the video, I had the same vector all the time, so it was constant.
Yeah.
But I'm going to show you here that it's possible to generate different faces for the same original one.
And second question, how big is this model then when you have trained it?
So this is about 12 million parameters, which is about 20 convolutional layers. So it's not that big. Yeah. Okay. So this is a demonstration that I made. And one thing I can, so I have this vector that says something about how the face looks. So I'm running this on my Mac, so it's probably going to be a bit slow. But I can generate different faces for the same original information. And what the actual model sees is just some cutout of the face. And this, you can see the face annotation right. So if I'm toggling this, I'm not sure if you can see it on the screen right here, but there's small dots right here that says that we're using the different landmarks of the face. And I can also take these landmarks and just slightly move them. And you can see so I moved my nose about here now. So you can do different transformations of the original face. Yes. To wrap up, if you're interested in learning more, we have 2 publications on this area. You can just search up my name on Google Scholar, and you should be able to find it. Also, we have an article on NRK, and if you're really interested in this stuff, you can take my course or the course I'm involved in, which is computer vision and deep learning. Yeah, thank you.
Thank you so much, Håkon. Do we have any other questions following up?
Have you considered an application using this, for example, to, I don't know, on the fly replace advertisement in a movie or something like, oh, this company hasn't paid for this advertising here, so you're going to swap it out? Or
Never consider it. It's probably possible though with this, yeah. I'm not sure if the thing with advertisement, you would have, you know what you want to generate, what you want to place in. So you have a 3D structure usually of a movie, so you could do some magic to place it in then.
Some more? Yep. Then we go to the last lecturer, which is Telenor with Gard and Vega. Yes. There. Yes. Yep.
Right, and then it's Windows 4 to get it. Okay, right. So. Yeah, hi, so I'm Vegard, and I'm here with Gard. So today we're from Telenor to talk about something we've been working on for a few months now. So we're from Telenor Research, from the AI team. So we're doing all kinds of AI research that's somehow relevant to Telenor. And a lot of that is about how to apply machine learning to business problems in the current business of Telenor. But then we have started looking into what does AI mean for IoT devices if we want to take machine learning models and put them onto IoT devices. And that's obviously relevant to Telenor because Telenor is deploying IoT networks, and we believe that in the future you will put deep learning models out onto these IoT devices. So we have carefully started to explore this field of tiny ML, which is an emerging research field now about putting deep learning models on microcontrollers. And especially in the last year, I would say this has really gathered pace. So, for example, Google is now publishing books on this topic. So we thought it was important that we, as a research department in Telenor, start to at least get a feel for what this is about. And that's what we've been doing for the past few months. So we wanted to show you what we have been doing. So we have familiarized ourselves with this technology by building a tech demo. So that's what we will show you. And then it also ties into this topic of surveillance that we will also touch on. So when we're talking about microcontrollers, we're talking then devices like this one. So this is just a USB cable, and then the thing on the tip here is the device. So I don't know if you can even see it on the screen. It's really tiny, right? So yeah. Did we get the next slide? Or, Almost. Just wait till we get to the live demo and then we'll see. Okay, so yes, putting deep learning models onto IoT devices. And we think that's particularly interesting in an IoT context. So IoT is about going out into the real world, and you want to kind of digitalize the real physical world. So you want to put sensors out into the world and maybe report that back to the cloud somewhere or something like that. And then you would typically do that by building expensive purpose-built sensors for a particular application, right? So you would make a temperature sensor, or say you want to count bicycles. Maybe you would then put a kind of inductive loop in the ground. So that's a very specialized sensor for that particular task. And maybe that would cost, tens of thousands of kroner, or, but if you can put deep learning models onto just these tiny embedded devices, and then put a trained model onto the device to do that just from a camera picture, then you could save a lot of money. And then that's kind of the idea here. And we're kind of inspired by this quote from Andrew Ng, this 1 second doctrine, because he's saying that anything that a human can do in less than a second, it's probably something you can get a deep learning model to do instead. So if you have an IoT application where today you have a very expensive sensor, but you could imagine swapping that out with a human that's just standing there observing, and then that human would be able to do the same task in less than a second. Say counting bicycles, you can do that in a split second. Then you could replace that with a camera and a deep learning model. And so we're working with these devices for our tech demo purposes. And as I said, these are quite cheap devices, less than 200 kroner. You get a 2 megapixel camera, and there's a microcontroller that can do some floating point calculations. And then you have the whole 4 megabytes of RAM and 4 megabytes of flash storage. So that's tiny machine learning. Can you put a deep learning model onto this and make it do anything useful? That's what we wanted to look into. Because if you can do that, then you can buy thousands of these and just place them wherever. So deep learning as a research field has started with big computers and big GPUs, and you use an entire data center to do your research because you want to squeeze the most accuracy out of your model. So you use lots of GPU hours. But now gradually that as you start using these deep learning models in applications, then you actually want to deploy it to computers, you want to deploy it to smartphones, and then it's more about how can you do inference in these networks without wasting your entire battery. And then when you get to these tiny devices, that's even less resources. So a smartphone might have, gigahertz of CPU, gigabytes of RAM, gigabytes of storage, and then you go several orders of magnitude down when you go to these tiny devices. So now you only have megahertz and megabytes to work with. And you maybe are running on a battery, so you need to also optimize for doing your calculations on the least amount of power possible. So that's really interesting from a research point of view. But why would you even do this in the first place? Why would you put tiny machine learning models onto IoT devices? As I said, you can do this really cheaply. So I think that's a good reason to do this in itself. Because you can do this flexibly. I mean, if you can do it with the camera and a machine learning model, then you could mass produce these generic devices. And they don't need to be specialized to your particular task anymore. You just swap out the model, but someone could mass produce these devices and make them really, really cheap. And then low power and low bandwidth, so you could place them where you don't really have infrastructure. And what I think is particularly relevant for the topic this evening is the privacy aspect here. That yes, you are putting a camera into the world to do something, but you take a picture and you process the picture on the device, run your entire model on the device, and the picture never leaves the device. And it's in fact just discarded immediately. So then maybe there isn't really a privacy impact, even though there are cameras involved. So I think that's an interesting question to ponder here is, when is it surveillance, and at what point does it just become a sensor? So that's the background on TinyML and why we think that's interesting to work with. So now for the tech demo that we have done so far. So as I said, we've been working on this for a few months. And our way of learning about this is to just grab the technology that's out there and try to build something with it and see how it works. So we took this device. Again, it's 200 kroner. You can go and buy it online. Ships in 48 hours. And we wanted to see, can you do object detection with this? So there's a 2 megapixel camera. That's quite good. Can we point this camera at something and get the model to tell us what's in the picture? So draw bounding boxes around the dog and the bicycle and the car. And for this, we used the YOLO model that was also mentioned earlier. Maybe we should look at adversarial examples. So basically, it's a plain convolutional neural network at the beginning, and then there's some magic at the end that generates all these boxes. But that layer is not that computationally heavy. So it's basically just a convolutional neural network computationally. And here's how it looks like. So we used a very, very reduced version of the YOLO network to make it fit onto the device. So one thing is you need to fit all the weights onto the 4 megabytes of storage. And then you need to make sure that all the activation values that you calculate as you run through the network can also fit in RAM at the same time. And so that's what you see kind of annotated on the slide here is how many kilobytes of weights do you have per layer and how many kilobytes of RAM do you need per layer, and then how many operations do you have per layer. And then when you get here, you have the magic YOLO output, but the rest is just convolution. And what is convolution? Just a refresher. So say you have your image pixels in blue here, and the trained network, the weights of the network are then these filters that we want to convolve over the image, which is basically taking this 3x3 filter and then placing it here, placing it there, placing it there. So you're sliding it across the image, and for each kind of positioning of the filter onto the image, you do a multiplication of the weight by the value, the other weight by the other value, and then sum that together. That's convolution. So it's just multiplying and then summing, but you have to do it a lot of times because you take all the filters and you slide it across the image. So this microcontroller is then going to be doing a lot of that. The performance of this device is surprisingly good if you just look at how many floating point values it can calculate per second. So we did some very rudimentary benchmarking here. But as soon as you, so I'm just showing you one example of what kind of challenges you face when you're working on these very, very tiny devices. So this is stuff that you wouldn't really be exposed to when you're working on laptops or smartphones, but it just really destroys your performance if you're not careful with it on these very tiny devices. So like you go from 27 million of these floating point operations per second to 1.8 million per second. As soon as you cross the cache limit, which is 32 kilobytes, which is not a lot. So what this means is that when you do neural network inference on this device, you really need to be careful about how you use your memory, is what we have learned so far. So just a very quick example, what we saw is that the order in which you do your convolution operations is really important because you want to access a continuous stream of memory. So if you do it in this order or in this order, I mean, it's just a matter of flipping the order of your for loops in the code. That's literally what we did, and I think that was a 3 times difference in performance, for example. So yeah, that's just parts of what we have seen. So we think this is a really interesting research field. It's really, coming as a research field now, and that when you develop applications for embedded devices with deep learning, there are so many other things to consider than just accuracy and how many GPUs do I need. It's more about what is the power consumption of this, what's the latency, how cheap can I get the device, does it fit into the RAM, and all that sort of things. So you see that in academic papers, for example, you need to trade off the SRAM usage and the latency and the accuracy and all these things, which is quite fun to work with. And then let's see for the demo then. So I'm just going to show you then the tech demo that we have developed. It will take a camera picture and then run this YOLO network and perform object detection and then tell you what it sees in the picture. Right, so that's, I think, 240 million floating point operations, and it will do it in 15 seconds. So it's it's not terribly fast, but it's quite cool that it's running on this. The microcontroller chip itself is 15 kroner, so it's basically free, right? So I'll just try to refresh the page to see that. Yeah, okay. So it's just getting its power from the cable right now. Everything is running on the device, and we're connected to it over Wi-Fi just to see the results. So this is the example image we saw earlier, and then we click Run Inference. And now it's calculating through all these steps of the network. Yes. So it says that there is a bicycle with 93% probability and a dog with a 94% probability. And I mean, I brought some pictures just so we can test. So, okay, I need to point the camera and then click. Right, so that's a cat. Okay, I'll just zoom out a bit. Yeah, so this is just our way of trying to understand what this technology is about. And then what could you use this for? Maybe you would want to use it for bike counting. And then you would need to think about how often do I want to take pictures? How much battery do I have? Yeah, so that's in fact a cat. Let's see, I do have a bicycle actually. Yeah. So yeah, so that's basically it.
You see if you can detect the people in the room.
Right. So let's just wait for these results.
Let's see if it's able to recognize everything in the picture first.
Yeah. Okay. Yeah. Sometimes it also sees the cat. Okay. Smile guide. Yeah. So I mean the topic here, AI and surveillance. If all this device is reporting back is the fact that there's a person in the picture, that's maybe not surveillance, then it's just a sensor, but yeah, there's people and there's a bicycle, yeah. Yeah, but as we get more cameras in the public domain around us, in the public spaces, is that surveillance? Is it just sensors? I don't know. I don't think we have thought a lot about that yet, but I think that will be an important discussion in the future. Yeah. So thank you. Any questions?
Thank you so much. Yeah, any other questions?
So are there, could you use TensorFlow on this device, or did you have to program it in C++ from scratch?
So this is actually TensorFlow, because Google have developed, well, they have developed something called TensorFlow Lite, which is you can take TensorFlow models and run them on mobile devices, smartphones. And then they will sort of use the GPU on the smartphone, or they will use specialized neural network hardware. So that's a quite neat software package that they have developed to complement TensorFlow. But even that is way too big for these devices. So they made something that's called TensorFlow Lite for microcontrollers. That's the name, and that's a C++ library that's sort of the bare minimum you need to run inference for a particular neural network on a device like that. Okay. And then we had to hack it a lot to get it to work. But it's
a little bit uncooperative. Once you start going against the grain of what they had envisioned, you quickly run into problems, let's say.
Yeah. So stuff like hacking it to make everything fit into RAM, freeing up memory as soon as you don't need it anymore. That's kind of the fun technical challenges of getting this stuff to work. Yes.
So, was it an ARM computer or an ARM CPU running in it?
This is actually an architecture that is not ARM, and it's the one I hadn't heard about before. But these ESP chips, what's it called? It's a weird not ARM embedded architecture. Yeah. So it was a bit difficult to figure out, are there vector instructions on this thing? Who knows? The documentation isn't that good. Yeah. So
you're running YOLO Lite on it, right? Does that use like depth-wise convolutions or?
No, this is just the plain convolutions. Yeah. No. But then I see that TensorFlow Lite for microcontrollers, this mouthful of a name, has all those depth-wise convolution. Yeah.
So we're also working in parallel on an ARM-based device for us to evaluate as a proof of concept, and it turns out that this device is pretty much exactly as powerful as a Cortex M7. Okay. Yeah.
Right.
Any more questions? Or no? Oh, thank you, Lord.
Yeah, thank you.
There, and I have to connect to the internet again. There. There we go. Yes, now all the lecturers have spoken. So, and now we're going over to some food from La Border, where everyone have ordered some type of dish they wanted of their choice. And so feel free to take all the snacks you want. There's a little bit more. And we're trying to hold they'll do to COVID-19 hold the restriction up like the 1 meter and use the anti-bac as much as we can. And else, just ask questions to all the lecturers will be here for some time, and we're brain here are also here if you have questions for us. So feel free, and yeah, thank you for participating.